All right, welcome LAC Cyberspace. You're all looking very well today. The paper here is Designing for Serendipity in a University Course Recommendation System. My co-author is Wei J. Jiang at Tsinghua University. So why are recommendation systems needed in higher education? One reason is that graduation planning is hard. This is a typical workflow you might find at any college USA. You have to look up degree requirements often on a PDF, figure out which courses you have and haven't taken, find the course that satisfies the requirement in the search, and then find availability in your schedule to enroll in that course. Besides degree satisfaction, exploration is also hard. And it's a kind of unique challenge among mostly American universities because American universities have a high degree of elective choice. There's a lot of electives students have to choose from. Also within degree requirements, there's a lot of options, and helping students navigate those options is something that requires advice. So students often ask, where should non-majors start in a new field, let's say data science, and how are courses conceptually related across departments? Often different departments and different instructors speak different languages in their course descriptions, so it's hard for a student often to parse out how two courses might be related. So on top of those challenges, there are broader challenges in the field that we resonate with and try to speak to and move the state forward with this paper. One challenge is how to deploy learning analytics like a recommender system while retaining institutional values. And Chen and Zhu from last year's LAC presented this as a challenge to the community, kind of value-centric learning analytics. So a context of this study is, it is an offline study. That is, we do modeling of historic data, but then there's an online aspect to the study where we test the models in the real world, our recommendation system. So this is our real world system. It's called Ask OSCE. It's linked to by the UC Berkeley registrar. You can kind of see it up in the upper right corner of the registrar's official class schedule there. It says Ask OSCE Beta. And this was developed out of National Science Foundation funding. So we tested the system a while back. This was published in 2019, but the survey was done sometime before that. And when asked if students at the university would use the system in the future, they largely said they would, 4.25 out of 5. But we also received informal feedback when we would present the system to administrators and students. And the feedback looked a little bit like this. This is just a sample. So one administrator said, we want students to find their own path, not follow others. And a student said, won't this result in only popular courses being promoted? And this is because at the time of this study, the primary feature of the recommendation system, or how courses were being recommended, was using a collaborative filtering based algorithm, right? So the typical people with your course history did this. And so these concerns were raised. Will that kind of algorithm not result in the values that UC Berkeley has of allowing students to find their own unique path? So we saw this as a challenge. Clearly there's a value here that we are not addressing, or is perceived that we are not addressing. So that brings us to the second broad challenge in the community we wanted to address, which is how to learn from the past without necessarily repeating it, right? So, learning analytics relies heavily on data often, but how do you train a model or leverage data to train a model without then having users reproduce that data in the form of a recommender system? So here's some values we identified at the university. And last year we presented a paper that helped address several of the values. This was a paper on helping students achieve a particular grade in a class by recommending them personalized preparation for that class. And then in this year's LAC, the presentation I'm giving right now is to address these other values. Wanting students to find their passion is a frequent value of faculty, and wanting students to get a well-rounded education is a frequent value of the administration. It's kind of pluralistic education. The university would find it to be a failing if a student graduated and all they knew was how to program really well, for example. They want students to be well-rounded. Okay, so how do we address these two, and what does this have to do with serendipity? In fact, what is serendipity? And colleagues have this, in the recommender systems literature, have defined serendipity to be a balance between unexpectedness and successfulness. Successfulness in a recommendation scenario would be, did the user click on the recommendation, right? Did they watch that movie? Did they buy that song? So how do you produce unexpectedness? A common approach to that is by diversifying the results in some way. So this could be choosing items from across several appropriate categories, right? Different music genres or subgenres, different movie genres, or in our case, different departments at the university. And it's often used in combination with some signal of user relevance. So it would be very easy to achieve just unexpectedness. Choose a random course at the university, recommend that to the student, very unexpected, but unlikely to be relevant to their interests. So if you just want to optimize successfulness, you can do that. In our case, successfulness would be a student wanting to enroll in the course we just told them about. And this has been the primary objective of most recommendation scenarios, right? They're trying to optimize successfulness, click-through ratios, consuming, buying, following. But if you only optimize for successfulness, you end up with something called the filter bubble, right? And this is over-personalization, over-fit, narrowing model of user interest. Judy Kay calls this stereotyping of the learner. And you could imagine this as, seeing a YouTube recommendation list that only has cat videos if you watched 2 cat videos in a row, right? You want some cat videos, but you don't want 100% cat videos. So we're trying not to recommend students 100% cat videos. So what is this going to look like? What are we trying to achieve in terms of a user experience? Well, we want a student to nurture a developing interest, but do so by being exposed to the plurality of offerings across campus relevant to this developing interest. And then we want students to explore those courses. So we're going to leverage a source of relevance, right? We can't just show random courses, by having the student enter in a favorite course that they have taken or are taking. In the latest version of our interface, we now have that list and they can just choose from it. But this is the only input. Nothing else is being personalized. We're not using their history for this interface, just the chosen course that is their favorite. And then we're going to generate results based on cosine similarity to this favorite course using a representation of courses that I'll get into, and we'll try several ways of representing courses. So here the student has selected evaluation of evidence, which is a sociology course on analyzing data from social media. And now we're showing one course max per department, and it has found data science connector course in letters and sciences, an introduction to urban data analytics and city and regional planning, ecological data analysis and environmental science policy and management, and then cartographic representation in the geography department. The description there is problems in representation of quantitative and qualitative data on thematic maps. So all of these have a data component. They all have a an analysis component. Okay, but how do we get there? And because of this fact that different professors and particularly in different disciplines kind of speak a different language, where are we going to find the similarity signal? Certainly catalog description is a start, but are there other ways of modeling similarity between courses? So as I said, we will try different approaches to modeling similarity, and one approach is representing a course with its bag of words catalog description. Seems like a basic approach that should be tried, a baseline approach. Next is another baseline, TF-IDF of that bag of words that weights words differently depending on how specific they are to that document, or in this case, course description, as opposed to how general they are, downweights the general words to hand wave that. But we also wanted to leverage catalog descriptions, but in a way that helps us understand the meaning or features of a course without using that history in a way that collaborative filtering uses to kind of perpetuate the past. So we want to leverage enrollments for informational purposes, but not for recommendation directly. So we leverage an algorithm called Skipgram, classical, almost modern, but by current standards, classical computational NLP algorithm that learns embeddings of words based on a large corpus. And in the past, we've applied this instead of to words to course enrollment histories to see if this could embed courses into a concept space the way words are embedded into a concept space. Right, so now you have a sequence of enrollments, and we have 10 years of enrollment data. So we have lots of sequences, almost 170,000 such enrollment sequences, and we run the Skipgram, which we call course to vec now, across those sequences to learn course embeddings based on context. Now we have made a modification to this algorithm for this paper specifically, and that is, instead of just learning an embedding of the course, in this case Spanish 12, we're going to also learn an embedding of other features that we have, other structural features of the course that we know of. So for example, we're going to learn an embedding of the department of that course, and we're going to learn an embedding of the instructor. And the hypothesis here is that, because all we care about is the course embedding, but by embedding the department and the instructor, we are kind of deconflating features of the course that are not most important to the content of the course, which is the similarity signal we're looking for. And also the hypothesis is, by learning a separate department embedding, we're now encouraging the course embedding to be a space that is this cross-departmental embedding, right? So you may have the department may be a very strong feature, but by having that department feature no longer be part of the course embedding, but be part of its own embedding, maybe now it forces the course embedding to have a universal concept space, not biased by the department, because we're looking for similar courses across department. Right? So we have this course to vec model and this course to vec plus, which we call multi-factor course to vec because of the factors of instructor and department. And then we combine the two, the bag of words, the content-based representation, and the enrollment-based representation, just simple concatenation of the two vectors. So to do the offline validation, which is to ask ourselves how good are these models of similarity, we needed validation sets for the offline validation, and we found two such sets. One was course credit equivalency pairs. So this is a list of pairs curated by the UC Berkeley registrar that says students can't get credit for both of these courses because they're so similar to one another. It could be an honors course and the non-honors version of it, for example. And so that is a very nice example of pairs of courses that are very similar to one another, and we can test our models against that. The second source was hand-created relationship pairs from earlier work, and this is where we had the honors course and the non-honors version, the online version and the non-online version, etc. And we could use these relationship examples of relationships much in the same way that the Skipgram paper with Mikolov used lexical relationship pairs in language to validate their model. Okay. And again, these are essentially the three main models we tested. So how it performed on the credit equivalency test, to perform that, we took one of the pairs, we said, what is the most cosine similar course to that course A in the pair? And then we looked to see how far down the list of nearest neighbors course B was. And so median rank is how far down course B was. And recall at 10 is saying what percentage of the time was the correct completion of the pair, course B, among the top 10 nearest neighbors. So in this case, TF-IDF was the best performing content-based model at 56.56 recall at 10. Course TVEC did all right. Multi-course TVEC did better, and the concatenation of the two did the best. For evaluating those relationship pairs, we used this analogy completion, like king minus man plus woman equals queen. And in this evaluation, the enrollment-based models did much better. Course TVEC and multi-course TVEC, 7.5 and 8.5, versus the best content-based model, binary bag of words, which is just standard bag of words, performing at 0.58. And then the concatenation of the two still does a little bit better at 8.7 versus 8.5. So now it's time for the online validation. And here we took we recruited 70 UC Berkeley students from across campus. Each student specified a favorite course they had taken, and then were shown 10 recommended courses, and they were presented in a random order, each of the 4 representation algorithms producing these 10 recommendations, and they rated each individual course recommendation. Okay, so to be clear about this, the randomization was algorithm order. Then for each algorithm, generate 10 recommendations based on the favorite course, have students rate. Okay, go to the next algorithm, generate 10, have students rate. And the questions we asked on the course level, so for every single recommendation, was for students to rate their agreement with the following 3 statements. This course was unexpected. I am interested in taking this course. I did not know about this course before. So we get unexpectedness from the first, and we get successfulness from the second. The more robust measure of successfulness would be, did they actually enroll in the course and take it? But it was not part of our protocol to be able to identify students and look in the future to see if they took the course. These were anonymous surveys. And I did not know about this course before. This is another factor we're looking at, which is novelty, but it's not part of the serendipity equation measure. So students also rated the 10 recommendations from a single algorithm as a whole, and we asked them to rate their agreement with the following. Overall, the course results were diverse, and the course results share something in common. Okay. So after 70 students went through this study, they had to be UC Berkeley students, and they rated the algorithms as follows. So the leftmost column is the representation model we're using for the course. So you see bag of words, and then you see the concatenation of TF-IDF with the multi-factor enrollment-based representation of the course, etc. Bin is regular bag of words. And then at the very bottom, you see RNN, and that's our old model. We did also test that as a bonus 5th algorithm that did not take into account their favorite course. It rather just said, students with a similar course history to yours took this next, and it showed them 10 results. Students did log into our system in order to complete that part of the study, so it was able to leverage their course history for that. So in the most important measure of serendipity, it was bag of words that performed strongest with 3.22 out of 5 in rating of serendipity, which is unexpectedness plus successfulness, in this case just the average of those 2 columns, and also scored very high in novelty. You can see TF-IDF concatenated with enrollment wasn't far behind. and had high diversity score. You'll see the div versus non-div. Div is when we show only a maximum of one result per department. Non-div is when we don't apply that constraint. So it could be showing 10 results from the same favorite course department. Okay, so for non-div, that maximized successfulness. So students were more likely to enroll in something if we didn't force this one result per department. And then the RNN had the lowest novelty by far, 1.8, if you can imagine. Have you ever, in your studies, measured a 1.8 on a Likert scale? So that was a wake-up call. And here you see the novelty broken out for the RNN by the rank of the course result. So the first course result had nearly 70% or more than 70% students strongly disagreeing with the statement that they did not know about this course before. So this collaborative approach to recommendation, turns out there's something to the criticism of that. What good is a recommender system if it's only telling you things you already know? And here on the left, this is the best serendipity model, which is just the bag of words diversified by department. And you can see, based on rank 1 to 10 of the course results, there's this tension between successfulness and unexpectedness. So as the results are less and less like the favorite course, unexpectedness goes up, but successfulness goes down. So having both of those high is very hard, and you need both of those high for successfulness, for serendipity, excuse me. So based on those results, we now use just regular bag of words to drive the diversity feature, and we use binary bag of words plus course of X for the within department matching. There is this dissonance. Why did the method work? Why did enrollment methods work so well on the offline data, but not in the online study? And we think that's because students only see the catalog description when they're shown a recommendation. So if the course to VEC model was picking up on latent features of a course, that won't be apparent when we show them the course recommendation. So maybe adding some latent features that we can infer to the results may improve the performance of the course to VEC models. So session-based recommendation, meaning RNNs, highly lacking in novelty and therefore questionable utility. Serendipity, very difficult to achieve because of this tension between unexpectedness and successfulness. The multi-factor course to VEC model, which was a novel model we introduced where we modeled the department and the instructor, did perform better than regular course to VEC. So in offline analysis, this was a sizable improvement, but it didn't translate to better user serendipity ratings over a simple bag of words approach. And lastly, this study highlights the importance of online validation, right? Had we stopped at the offline validation, we would have declared victory, for having introduced the multi-factor model. But doing a real study with users informed us how we might need to add to the design of the experience to really benefit. Thank you.